Hey everybody, this is Sujit from IIT Madras. So critical transitions in complex systems, what we call CTCS webinar series, is being jointly hosted by IIT Madras India and by Potsdam Institute for Climate Impact Research in Germany with Jürgen here, Jürgen Kutz. This seminar series brings together experts from fields, very diverse fields such as climate science, fluid mechanics, neuroscience, ecology, etc., and all linked to nonlinear dynamics and complex system theory, and aims to disseminate the state of the art in the prediction of critical transitions in these diverse fields of study. And the webinar takes place every month on the last Monday of the month. So mark your calendars. And before we proceed to introducing the speakers, two housekeeping notes. First, I request everyone to turn off their microphones so that we have a smooth seminar. But please type your questions in the Q&A box in Zoom, and the speaker will answer the questions at the end. There will be ample time at the end for clarifying your questions and whatever else. So with this, I now pass on the floor to Professor Jürgen Kutz, who will introduce the speaker.
Yeah, wait, I was muted. Now I'm here. Okay. Yeah, hello, everyone. I'm very happy that we have again our seminar today, and I'm really very happy to introduce my very good friend and colleague Celso Grebocci as a speaker today. You all know him. He is a real pioneer in nonlinear dynamics. Let me give only a few keywords, what he has really done, what he has invented. This was chaos control, communication with chaos, fractal Bayesian boundaries, strange non-chaotic attractors, and of course, also related to the topic crisis. This was already 40 years, 30 years ago, and very highly cited papers. But he is not only a pioneer, he is very active, has been very active over all the decades, and still today, of course, producing a lot of new results, initiating new research. And we are really very happy to have him. He is now 6th century professor, chair professor at University of Aberdeen, is member of several academies, got important awards, and highly cited, all these things. I will not steal his time. It would be longer than his talk would be. This is not what we would like to have. I would like to give him the floor. Celso, I'm really very happy. Please.
Jürgen, thank you so much. Indeed, Jürgen is my friend since 1988, many years working together, interacting, and thank you very much, Jürgen, for the invitation. Also to the people in India for organizing this talk. Anyway, and I'm talking about crisis, danger and opportunity. The Chinese use two symbols to express the idea of crisis. These are the two symbols that comes from the Qin dynasty over 2,000 years ago. And basically, it means danger and opportunity. The idea is that at the crisis, one can have either, depending on the direction when one decides to move. And this was exactly the meaning when we chose the name to name crisis the dynamical phenomena in 1982. Is this idea of danger and opportunity, creation and destruction. And I put a subtitle here in the highway to climate hell. It applies to climate change. Like crisis, it conveys the idea of a critical transition applied to climate change. Like crisis, and is the danger opportunity choice associated with global warming. Danger means you progress in this highway as we've been doing, and opportunity, perhaps you take a ramp off the highway and try to reverse the trend. For you to see how the situation now is scary, let me show you this. The global warming now is pushing ocean temperatures off the charts. And in March 2000, 2024, it was the average 21.07 degrees centigrade. Is this high? Let's see. And what I have here is the global sea surface temperature, waters, top of the sea, the average from 1982 to 2023, and deviations from the mean, from 1991 to 2020 mean. Is the mean, and here is the deviation from the mean from 1982 to 2023. And look, in red, what happened in 2023. Incredible, completely off the chart. Completely different from the other temperature anomalies. Here I am plotting the actual temperature, the temperature since 1979 in degrees centigrade. You have here an increase, an average increase because of the summer in the southern hemisphere. Then that happens in February and March. Then in July, August, because of the summer in the northern hemisphere. But look here, suddenly in 2023 is really above the previous temperature, the previous oscillations. And you have to see that the ocean, it covers 70% of the planet and have kept the Earth's surface livable by absorbing 90% of the excess heat produced by carbon pollution from human activity since the dawn of the industrial age. Then you can see this is quite dramatic, what is being happening. Well, this is sea. What happened to the surface temperature? Here in this year, it reached 1.68 degrees centigrade. And this is quite incredible because, look here, what I have here in the abscissa, I have the pre-industrial level. It's here at 0. And those are the temperatures that are warmer than the pre-industrial level. Look here, March 2024, 1.68 degrees. Is really quite above, the pre-industrial level. And what I have here, again, I have the pre-industrial level here in the abscissa from 1850 to 1900 is here. And those are the historical temperature 1940 to 2020. Again, this is the same thing. Again, I'm off the chart. 2023, 2024, 1.68 degrees above. And of course, because of this, the top layer of the ocean holds so much energy. And because of that, we have droughts, we have flooding, we have hurricanes and extreme weather. This is in Brazil, Porto Alegre, in Brasilia. And there live 1.5 million people, and they were displaced. That was April 2024. And but look here, what's happening. And I was even in Germany at that period for a meeting of the Max Planck Society. The United Nations published a report on international migrants in the world. That was in June 14, 2024. Now, it's June 14, there were 281 million international migrants. And this does not count like the Brazilian here in Porto Alegre, it does not, because there were these internal migrants. But this 281 million international migrants include people that are migrating because of climate change. And this is 8 July 2024. And here comes the report from Associated Press that date was 12 straight months that the world temperature was above 1.5 degrees. What means 1.5 degrees? You have the Paris Agreement, in which the idea was to limit the temperature to 2 degrees above the pre-industrial level at the end of the century. But the idea was really to limit to 1.5 degrees above the pre-industrial level. And you see, we're in 2024, a quarter of the century is already 1.5 degrees above. And this is for 12 months in a row that's happening. The president of the United States was Clinton, ignoring climate change is deadly dangerous, irresponsible. Climate fuel extreme weather events don't just affect peoples, but they cost money, hurt the economy. That's very funny because the United States is the biggest polluter, and the United States decided that they should get out of the Paris Agreement because that will bring permanent damage to US economy. That was the president saying that in 2017. In 2020, United States came out of the Paris Agreement. And I should be fair that they joined again. Until today, the Senate has not yet approved the agreement for ratification as a treaty. Then this hanging on the balance, okay? And perhaps there's all these bad things, all this danger and so on. This came published on the 22nd of August, 2024, New York Times. It seems that the worst case disaster for Antarctica, it looks less likely. Is the following. The belief was that you have these sheets that are breaking, going to the ocean, and after that ice sheet break, you have cliffs, 4,000 meters high of ice. And once the breaking of this plateau, that big mountains of ice will collapse into the ocean. It seems now the studies are showing that perhaps that is not going to occur. That's what's going to show. But the situation is not good. For instance, you know, with the rising temperature, permafrost, for instance, in Siberia is causing problem. There's a release of methane and other carbon products, okay? Then the situation is not really good. And let me do the following. Let me show here what I call the social and ecological drivers. And here what I represent is a visual framework for sustainable development. What it means. I have here this donut. This donut has two boundaries. It's the ecological or planetary boundary and the social boundary. The inner center here, the inner part, represents the proportion of people on Earth which lacks access to basics. Basic like food, health, political voice, networks, and so on. And the ecological boundary is really the planetary boundary that you should not overpass because humanity depends on that for its survival. It should not be overshot. It's climate change, ocean acidification, chemical pollution, nitrogen, phosphorus, freshwater withdrawal, land conversion is quite important, biodiversity loss, air pollution, ozone layer depletion, and so on. Then the social drivers are the 12 social aims of the Sustainable Development Goals of the United Nations. These are the 12 here. And the 9 ecological drivers are the planetary boundary that Earth system depends on, and the safe and just space here in green. That's what it is. That's where we want to be, where Earth should be. But look here. If I look here in red are the planetary overshoot, the ecological overshoot, and inside the proportion of people on Earth that lack access to those basic elements. Then these are the current social shortfalls and ecological overshoots indicate a planetary regime shift in which the Earth's biosphere may undergo a tipping point or a regime shift. What is regime shift? Regime shift is where there is a qualitative change in the dynamical state and occurs suddenly, without warning. It is particularly devastating because any understanding of the system based on observations made before the regime shift becomes irrelevant. The time of occurrence is highly unpredictable, and it often results in population collapse and species extinction. Let me explain this, okay? What I'm going to plot here is the global ecological state of the Earth versus one of the drivers. I chose the land conversion as the fraction of the ecological system on Earth that experience land conversion to urban and agricultural development. That's what it is. If you look here, for instance, year 1800, there was 1 billion people. And the amount of land conversion depends on the population of the Earth. In the year 1800, 1 billion people. Then in dark green, I don't know if you can see, there is a small circular sector. Then it's a very small part of the Earth that suffered irreversible change because of land conversion. When you come to now, 50% of the ecosystem went over this land conversion. And it is anticipated that in 20 years, the population of the Earth was going to be 9 billion. And the ecosystem is going to undergo a tipping point. It's going to go from a survival state to an extinction state. Many parts of the ecosystem, many elements of the ecosystem. And this is mimic here. This is called the resilience function. From the dynamical point of view, what I have here, I have the survival state. Then there is a reverse saddle node bifurcation. From here, there is a probability that the system is going to collapse and going to go to the extinction state. Then from the extinction state, if you improve the environment considerably, you come to forward saddle node bifurcation, and then you can recover. Then you can see you have to work very hard for that to happen. There is a hysteresis here between the collapse and the recovery. What we have here, we have two attractors. We have the stable state here, which is the survival state, and you have the other one is the extinction state. In between, there is this unstable boundary. Then the dynamics here, if you perturb, you go back to the state. If you perturb here, you go back to the extinction state. Of course, perturbation is large. You can jump over this boundary. You can go between both states asymptotically. These are the basins of attraction, the extinction, the survival state, and this is the extinction state. Anyway, this is one of the pictures, studying in terms of simple bifurcation diagram. But there is another one, a situation much more worrisome, is associated with crisis. Then there is a critical transition lead to regime shift. Critical transition will be at the crisis, in the regime shift after is the waiting for the system to go to a collapse state. And this can happen a period of relative stasis. Stasis means no further deterioration. The environment can be as it is, and then can lead to that situation. And then what I plot here, let's say the ecological state, I call Y, versus the change in which measure deterioration of the environment. What I have here, then is a nonlinear system, nonlinear stochastic system, there is noise, but there is this sustained dynamics. If you're before this boundary crisis point, you have sustained dynamics. The system has this kind of nonlinear behavior, stochastic behavior that we have, that we observe now. Okay, there is a volcano, there is this, winter, summer, and so on. But suddenly there is a crisis, when you go beyond that crisis, beyond this regime shift, beyond this critical transition here at the crisis, I have a transient. Suddenly there is a regime shift, then you can go into collapse state. And this is a contra point to the simple bifurcation, because the time it takes here is exponentially distributed. Then in some sense, when you're in this point, you're in this Lorentzian waiting for the collapse of the system, for the regime shift into a collapse state, into the extinction state. And this is very serious. In one of the global warming conference that happens every year, the Secretary General warned that Earth past this point of the call a point of no return, then past this transition, this critical transition. Now you're in the state waiting for the regime shift into the collapse state. And then the situation is quite serious. That's what he's warning. Okay, and we know, I just mentioned the permafrost. Even without any further increase in temperature, there is, according to the release of methane and other gases, and the situation is serious situation. Okay, then let me tell you, in dynamical systems, you know, if you study dynamical systems, you have to study in terms of invariant sets. And the chaotic transient, the transient chaos of the transient is governed by a chaotic saddle. And the chaotic saddle is the set that happens after the crisis. Let me go here. Then here is a simple one-dimensional system. There is a tangent bifurcation. You create this unstable periodic orbit. It is the stable one, which goes through a bifurcation, periodic bifurcation. And at this point, there's a collision with the attractor with the boundary, because here is the basin of attraction. The other side here is the basin of the collapse state, which in this case is minus infinity. Well, once you go beyond, you have a transient chaos. You have the transient state. Then this is exponentially distributed, but suddenly the trajectory goes over this unstable point. It goes to a collapse state. And then crashes this collision of chaotic attraction with the boundary of its spacing. Okay. Anyway, then let me look again at this diagram. I have, let's say, the global ecological state versus the parameter. By the way, you can get the transient in each periodic window. Because we're a dynamicist, the periodic windows are dense in the parameter. If you take a value of the parameter for which you have chaos in an arbitrary closed neighborhood, there is a window. And by the way, Jim York wrote a paper, period 3 implies chaos. He was talking about the chaotic set, this transient chaos in this region. And that paper gave the name to the phenomenon and also gave the name to the field. Chaos, you know, is the official name of all the societies and so on. And you can see that indeed you should have this complicated chaotic set here. Because if you're here, there is infinite number of aperiodic chaotic orbits. Also, a finite number, it's countable, the infinite number, countable number of unstable periodic orbits. And if you change parameter, all of them are here, only they are in this chaotic saddle. When you go beyond the crisis, again, you have a chaotic saddle here and associate what they call transient chaos. The time to decay, the waiting time is a power law. You can see the average time goes as 1 over p minus pc to some power gamma. Gamma is positive. Then when p approach pc, since there's a denominator, the transient time goes to infinite, of course. because you go in direction of the sustained chaos. When P goes to PC, the transient time gets infinite. There is another situation that's quite incredible. It's associated with long-lived chaotic transients. There's something that we introduced in 1983. And what I have here, the system, here is the real numbers, here is the circle go between minus pi and plus pi. I have a chaotic attractor here with fractal structure. And this is the Bayesian boundary, which is fractal. This is the pre-image of the boundary. And in this case, just in this example, I have a period 1 orbit here, unstable. There is a period 1 orbit unstable there, and they coalesce. When they coalesce, they form a needle. Then now what I have here is a transient, because the trajectory can leave the set through the needle and goes to plus or minus infinite or to some other attract. It does not matter. But you can see this needle is so narrow and is so unstable transversally here that the orbit has to be precisely almost in the center of the needle, because this transversal instability is going to push the trajectory to go sideways here and will not go. Then the transient is very robust, and you can change the parameter quite a lot. Still, the transient is very long. And in some sense here, when the parameter approaches the transient, because the time here is exponential distributed, and when the parameter approach the crisis value, the time increases more rapidly than any power of the inverse alpha minus alpha star. It's quite incredible, this. And this is very important, because if you look now at the work done in ecology, the simulations, the models and observation show that the long transients now is occurring in ecological systems. This is very bad in order to plan, to manage ecological systems, to manage the strategies of ecological systems, because the strategy of ecological systems are based on the fact that the system is stable, is asymptotically stable. But then you're studying some ecological system, you think the system is stable, but because of the long transient, suddenly it goes into collapse state. Then this is giving quite some difficulty for ecologists, is the fact of the long transient in dynamical system, long transient ecological systems. Anyway, how can when one knows that we are in a transit? Can the system collapse be anticipated? What I am doing here, I have a population evolution in a chaotic food web system. The food web system as the consumer, the resource, and the consumer, which is the resource, and the predator, which is the consumer. Anyway, it's a three-dimensional system, and I'm plotting here the predator versus time. I have two time series. One is sustained dynamics. Another one is a transient. Then how can I tell that I'm in this, either in sustained dynamics or in the transient, just based on data? If I look here after time 3000, they look the same. They're statistically indistinguishable. I look at 6000, still statistically indistinguishable, until about 8500, let's say. Then suddenly they separate, they diverge from each other. Then the prediction of crisis, prediction of this critical transition, from assuming that we don't have the equations, but based on data, is one of the perhaps most difficult problems in nonlinear dynamics. And for instance, if I look at this time series, how do we know that the system will be okay for this parameter value? Here, how do we know? Look the same, it's statistically indistinguishable. How do we know that the system is already in a transient? It will collapse in the near future for this parameter value. How can we do that? totally data-driven method. You say, I just gave you this, how can you distinguish that? There are two ways we can do. One is using sparse optimization that we did about 12, 15 years ago. Another is machine learning, which is very modern, with people using a lot in artificial intelligence and so on. What's our previous method and we work was sparse optimization. Then in that case, we use compressive sensing to find the system equations from time series. But it's effective only if the system equations have simple structure. What it means, they only contain a few power series or Fourier series terms and their vector functions. And this can be quite a problem. Let me show you. For instance, how do we do that? For instance, compressive sensing. Let's say I have a network. I can get small amount of data, but really small. It's a compressed set of data in each node. From that, from this measured time series, I can the structure and the dynamics of the network, and the structure of the network and the dynamics in each node of the network. Or I can do something simpler. I can, for instance, if I don't have a network, I can get the topology of the dynamical equations. For instance, you gave me some system, like the food web system, and you gave me a few points. And for those few points, I can get the dynamic equations. And from dynamical equations, using just data, I can predict the crisis. For instance, with 8 points, it's enough to predict the crisis with 10 to minus 3 precision. It's quite incredible. It's the size of a pixel here. But for that, how can I apply? How can I use sparse optimization? Then there are three cases that typically occur. In two of them, I can do, for instance, the vector field map, the equations that I don't know, but in principle, they should have few Fourier series terms or few Fourier power series terms. I can do that. Then let's say I take pendulum equation, I take a no map, this kind of simple system of food web systems, or then I can do. But if you take something a little bit more complicated, this is the Ikeda map. If you look at the face, the dynamical variables appears here in the denominator inside the sign. Now, if I want to expand that in power for a series, whatever I want, suddenly I have an infinite number of terms. Then we cannot do. Then in this case, instead of using sparse optimization, compressive sensing, we use machine learning. Then perhaps you know machine learning much better than I, but let me tell you a few systems here. Let's say we do reservoir computing, simpler. And what I have here is the reservoir computed here, is the hidden network. I have the input channel, which is going to be the input to the reservoir, and the output is from the reservoir to the output channel. Then initially, this is an open loop system because I'm using data to train this network. Once I train this network, now I can connect the output to the input. It becomes a closed system. And this closed is a self-evolving dynamical system. This virtual system is self-evolving. And I can make prediction. Then I can iterate the system and look what is happening for a few Lyapunov exponents. But you can see, when I train the system, I train for a fixed parameter set. I choose the parameters and I do the training. Then what I have here, I have a dynamical systems for a fixed parameter set. And if I look at the evolution of the system, I look at the evolution of the system for that fixed parameter set. But if I want to predict crisis, then I need a little bit more than that. I need to predict the dependence on parameter to enable the machine learning prediction of crisis. Oh, I'm sorry here, what I'm doing here. The prediction of crisis that leads then to transient chaos and collapse, or prediction of critical transition that leads to state shift, then collapse. What I do, I have to allow the machine learning to have the ability to assess the dependence of the dynamical system on the parameter. And in order to do that, about 2, 3, 4 years ago, what we did, we endowed the machine learning with a input parameter channel. Then with this input parameter channel, we can make prediction. Then we train the machine learning in a few values of the parameter, in this case, before the crisis value. And in using that, we can predict the dynamics before the crisis, after the crisis, and the crisis point that we can do. And let me show you. Then I'm going to give 3 examples now. One is species extinction, a chaotic food web system. Then again, I have the resource, the consumer, and the predator. And here's the system. It's a simple system. And I'm going to train for this parameter value, that parameter value, and that one. And I'm going to make a prediction trying to find the crisis point here. It's in black here. And look here what's happening. And what I have here, I have the dynamical system. I'm using the equations. I take the parameter value in which I have sustained dynamics. I take a little bit different value, and I have a transient dynamics. Now I'm doing the machine learning. I'm taking the same parameter values in machine learning. Again, I get sustain, and I get transient here. And what I take here, I think it was 500 resolution of the machine learning and try to predict the crisis value. And I do here the prediction of the crisis value, this critical transition with 10 to -5 precision using the statistics of this histogram. And I can do more. What I can do, remember, if you read the paper of Lorentz, he plots the maximum of this chaotic, the Lorentz attractor, the maximum now versus the maximum before, the current maximum versus the maximum that happens before. I do the same here. I plot in this case, I did the minimum now versus the minimum before. And I have a region here and given by this square here, this dotted square is where is the invariant dynamics. This is used in the equations before the crisis, because this is contained in this region, but after the crisis, this goes over this square here, and now the system can leave and go to a collapse state. But when you're doing the machine learning, it happens the same thing. Here it is, and here is the state of collapse. This is the same thing is happening, because the machine learning is predicting that equal. I can predict also the distribution of transient time. Now I'm looking beyond the crisis, and I take a lot of realizations at different points of the parameter and getting the distribution of transient times. And here is semi-log scale, because there is log versus linear, and this is a power law. That's what it is. It's a Lorentzian distribution here. And remember, I said that the Ikeda map, this optical cavity map, I could not use using sparse optimization. Now I'm using a machine learning. This is before the crisis, using the system. Here before the crisis, after the crisis here. Now machine learning. I do that. I can do also using machine learning, predicting then the dynamics, the transient dynamics beyond crisis. Also, I can find here the transient time and so on. But not only that, I can also do the spatial temporal system. What I have here predicted the transient dynamics in the Kuramoto-Shivanshinsky equation. Is a spatial temporal system. Here I take the real system in which I have a sustained chaos, turbulent dynamics, and here is this crisis point here. And this is the same value of the parameter here. You see, this is machine learning, and this is the predicted from machine learning. Is the transient dynamics, okay? And okay, then let me just indicate there is a paper here. We don't discuss machine learning, but we discuss different techniques, including compressive sensing. We published this in physics reports about 5, 6, 7 years back here. Anyway, to take home the message, transients are ubiquitous in ecological systems. They're so important now. And long transients, I mentioned, have implication for management of ecological systems, to design strategies for the management of ecological systems. Often a transient is followed by a system collapse. It's important to be able to predict future collapse while the system is still okay. We want to do that just using the data. Can we do that or not? And that's what I'm saying with machine learning, we indeed can. Then the prediction must be based on data from current normal state of the system. And applicability of sparse optimization is limited, as I argue. The machine learning is a powerful alternative. It can be exploited to predict critical transition, transients, and system collapse in ecosystem. And due to global warming, some natural systems may have already been in a transient state, awaiting catastrophic regime shift to occur. And here we're talking more in the sense of ecological systems. And anyway, thank you very much for listening to this talk. And if you have any question, I'll be happy to address, to listen to you, to have your opinions. And I have Jürgen Kurz, my friend in the audience, is top person in global warming and climate change. Thank you very much.
Thank you very much for this very nice talk. And I request the audience to type in your questions in the Q&A box.
May I ask without typing?
Yeah, sure.
Question. Celso, a bit strange question. Suppose that we are really will go to some collapse. I think afterwards will also something happen. What do you think? What should be remaining there? Some memory, some unstable periodic orbits or something to really try to stabilize something? Do you see some chance or zero?
No, in this picture that we're having, there's not that, okay? But if you look at this picture of the crisis, the transient, all the dynamics is there. You know, the dynamics, we can use the machine learning. The same, let's go back. I did this machine learning with parameter. In this case, I trained the chaotic set. Then I cannot predict the periodic orbs there. Does not make sense because I'm not training the periodic orb. But I can obtain the saddle there. I can obtain the saddle. I can get this chaotic saddle there. But let's go to the crisis. And the machine learning is getting the dynamics as it was the sustained dynamics, but it's getting as the full chaotic dynamics. It's getting at the invariant chaotic saddle. This chaotic saddle has the stable periodic orbit, says the stable chaotic set is there, is better. And this would be very nice to explore that. No, the people did in dynamics that, but never in this context of critical transition and regime shift. And you know, the people in ecologists, if you look at their papers, there's no much on in dynamics there. And this is quite open, you know. And not only that, there is some issue here that I did not discuss. If you look at the transient, I cannot train doing what I was doing, trained in machine learning in the transient state, because in training, I need almost infinite, the data train should be infinite. I don't. But now there are some works coming in which perhaps you can do that, train that using what they call metadata. Basically, you take a statistical set of data in order to train the machine learning. And in this sense, what you're doing, you're restricting the dynamics to the transient. And you can do that, because you can extract the dynamics, you can extract the stable periodic coordinates, you can do, and not only that, there are some papers that came before look at the transit or to use the control of chaos, but this is much more the control of chaos, no? The control of chaos and when you have the transient, how can you control that dynamics? I think perhaps we can combine both, but now thinking about this critical transition and regime shift, I think would be. Yeah, that's a very good question, that use the to get information from this chaotic saddle. Because in terms of dynamical systems, we have to look at the invariants. And the invariant is the chaotic saddle. And the chaotic saddle contains all this information that you're asking now.
Thank you. Thank you.
There is one question. It's really a comment in Q&A box. Can you see it?
It's at the bottom. Yeah, in some sense, I'm so limited in finding this. I cannot see.
Maybe you read it, Sujit.
Yeah.
Okay.
Can you read? Yeah.
Yeah, so this is, it's from Cristobal. He says, not a question, but I would like to send greetings as we applied OGY method of chaos control in plasma physics at UHP Nancy, France, many years ago. So that's
Oh, thank you very much. Very good. Oh, yeah, this is so important. Just came an article in Physics World about the control of plasmas and ether and so on is a major problem. My goodness, that. Okay, thank you very much. Yeah.
There's a question from anonymous attendee. Is there any evidence for cascades of period doubling, bifurcation, chaos, crisis, transient chaos playing a role in climate change?
Well, you have these transitions. I showed two pictures here. One was the one was the saddle bifurcation, and the other one. The other one was talking about there is a state now, and you're going beyond this critical transition. I'm not looking. I don't know even if there is. My goodness, I don't know. I'm really concentrating the crisis. I'm not an ecologist, and probably there are works on that. I really don't know. I think there are. If you go back to one great ecologist was Robert May. That was in the 70s already. And he was doing the period doubling. Yeah, of course. No, he was already looking at the period doubling dynamics before Feigenbaum. He did that. And was so, he died recently, by the way. He was referred so much as one of the leaders in the use of dynamics in ecology. And the dynamics that he used was initially what we call the period doubling dynamics. I think should have quite a lot of work on that. I'm not familiar, okay, because I don't deal with that. Yeah.
Okay, thank you.
Yes, look at the papers, by the way, of Robert May and follow-ups. Okay, there is so much refer. He was even the president of the Royal Society in London and extremely well-respected ecologist. Yeah.
Okay, thank you. Professor Ambika, you can ask.
Yeah, I just have two questions. One is, there is another type of crisis that happens other than boundary crisis. Do you think that also has some relevance in these cases?
Yeah,
transients?
that's what I mean. In some sense, when I look there, I really didn't look at this interior crisis,
Correct, yeah.
Here. Yeah, here.
Hmm.
Yeah, because if you look here, you have bands here, 3 bands of chaotic sets.
Yeah.
Suddenly, at this point here,
They
there was
merge and
another attractor
yeah.
which collided here. You have this
Yes.
interior crisis here. Okay. And the machine learning, if you train before, you can predict that point. Very easy. Okay, you can predict, not at that point, you can predict even more. For instance, if you go back here,
Yeah.
there's another attractor here. Because there's higher dimensional, there's another attractor here. You can train the machine learning in this set, in this attractor, then you can predict this point in which there is this collision.
Celso,
here.
we do not see this.
Yeah,
you
it's
can
not
see.
shared. It's not
You
shared now.
should bring it back.
Yeah.
Yeah.
Oh.
Please
I
share
have
again.
to share again.
Yeah, thank you.
Wait, how do I share again?
Yes.
It's share, okay. Yeah, okay. Sharing.
Yeah,
And I think I have to do more than sharing here. Share,
So we can see it.
now we can see.
okay. Okay, let me go without this. Okay, let me. Now it seems that there is another image. I'm sorry here. And okay, let me go back here. Let me go to. Just a second. This here. Yeah, you look here. Yeah,
Yes.
here this interior crisis. Okay,
Yeah,
basically
that's
there's a collision of two attractors. There is
Yes.
this attractor here, the main one that you can see. Then suddenly it took over here. Okay, but there is another one here that went to a period doubling here.
Yeah.
And you can train the machine learning in this one that has, I don't know how many pieces here now, but
Mm.
clearly there is one piece here, okay? And what happened when you train here, the machine learning is going to predict the point in which is going to collide here and is going to merge with the other attractor.
Yeah.
Okay, that's what's happening here. This is the
Yeah.
interior crisis. You can see it here. Also,
Yeah.
there's a point here, okay? Also another one there. That's what's happening, okay?
Yeah.
And I was more concerned, also was talking about this transient here, which is associated with this subduction, because you have crisis here, suddenly there's this subduction going into a window. And this machine learning can predict too, that, okay?
Okay. And another question is,
Yeah.
in cases you are using data-driven approach and you cannot get the equations, in such cases, do you think some of the embedding techniques or reconstruction of dynamics will help?
Okay, wait till I'm fight with this stuff here. Can you ask again the question? Sorry.
Yeah, so in case you are using some data-driven approach, as you mentioned, but you cannot get the equations for some
Yes.
reason, but still there are other methods like reconstructing the dynamics. Will such methods help in predicting the crisis?
No, that's right. That's the idea. The whole idea is that we don't have the equations, okay?
Yes.
And we're training, we have data. You don't know if it's any. Yeah, that's what the people now are working. In Shanghai is working that, but that you have a data time series.
Yes.
And from that time series, you take that time series, and from there you train the system. And that's a question, you know. If you look at the system, will be a few parameters you have to train in order to get the critical transition. And because if you have only one time series now, the state of the system, you don't have that time dependence. No, the only thing you can do is to predict if you're beyond the critical transition or not. Okay. Because if you look in the ecological system, the system in some sense is a fixed set of parameters. No?
Okay.
This is quite interesting because if you look what's happening with the many ecological systems, now there is such changes that's occurring in ecology, and there are time series available now, a year ago, or before. And from that, you can train the machine learning in order to find the critical transition point and go beyond and look at the transient and look when the regime shift is going to occur now. And that is possible to do now. Yeah. They're based on historical data. Okay. But you need more than one parameter value, more than one instant in time. Yeah.
Okay, thank you.
Okay, there are a couple of more questions. One from Mr. Jayesh. Apart from deviation from a mean or stable state, are there other features that can warn of a critical transition?
Another that can model what?
That can warn about a critical transition.
Oh, in some sense, I'm not really looking at the average. What I did there was the statistics. Okay, then we really, once you go beyond this critical transition, you don't know how much beyond you are. Okay, you have the critical transition, you're making there. The only thing you know that this transient has this kind of behavior. You know, if you have a low dimensional type of system, it's a power law. It's the distance. Then the only thing you know, you're in this Lorentzian waiting that something is going to happen. And then that's the reason comes all these arguments. And you take the president of the United States at that time, now is back. He's saying that this is not going to occur. We should forget about these things, okay? And but you take the Secretary General of the United Nations said, no, we already passed this point, the critical transition. We are already in the point of in which a regime shift is going to occur. In that state, we're going to have the regime shift. Okay, we're in this waiting for the collapse, this Lorentzian waiting for the collapse. No, then and that's the discussion. No, you can see it. We had just the COPs now, Azerbaijan, and people even did not show up. The major president, governors, and so on, because there's this now. Whatever is going to happen. No? Perhaps Jürgen can have some comment on that. Yeah.
Okay. There's another question. How can we train the machine learning method if we don't have data after the transition?
Yeah. My sound there is very bad. Can you repeat again? I apologize to you.
Yeah. How can we train the machine learning method if we don't have data after the transition?
Well, this was the question that was asked before. No, the data, you know, according to the machine learning that we have now. Don't forget, the machine learning up to now was fixed parameters. Only now we introduce machine learning in which there is this dependence on parameter. We introduced this input parameter channel. There was nothing about that. All the machine learning was done for a fixed parameter. Then you look at the evolution of the system. And now we're trying to find out how to deal with this parameter channel. And we did the training now, showing, of course, those models in which we have the sustained dynamics, the normal behavior, only train and make all the prediction, and we can look at the transient. We get all the statistical distribution. So now came a paper, was not published. I know the paper was written and was submitted to physical review letters, not published yet. I don't know if it was accepted. I'm not involved in that, in which they're looking at data beyond the critical transition, beyond the crisis, how to do the training beyond. And basically use what they call in this paper metadata. Then you have to look at the combination. Is it train the system where you don't have if you take a value of the parameter, there is a transient there, then there's a statistical distribution in the data, and you try to do that. This is research that's going on. That's your question about, yeah. Okay.
Okay, thank you. There's one more question. Transient chaos can occur after periodicity or chaos. Which is more sensitive?
You mean the chaos, or you mean based in terms of Lyapunov exponent, exponential divergence?
I don't know the.
No. It's the
Yeah.
no. If you go beyond here,
Yeah.
if you go beyond, it's the same that if you look at the Lyapunov exponent, if you could, Lyapunov exponent, you need infinite trajectories. But let's say you look at finite time Lyapunov exponent, you look before the crisis and after will be the same, indistinguishable. There is a small change only, okay? Then this chaotic set here, this chaotic saddle, just after the crisis, very robust. Even if you plot, it's going to look, for example, because here what I have is a projection. I projected this in one dimension here. If I take away, now I look at higher dimensional space, I look at the set before, and I look after, they look the same if I'm very close to crisis. I need to move quite away in order for me to get what is called a thin, very thin, not thick, thin chaotic saddle for you to see, oh, I have something that does not look as sustained dynamics, okay? And if you go even to long transients that I show you, you can go much beyond the crisis point, and the dynamics looks the same. I can go much beyond there, and I have the chaotic dynamics here. Okay, will be the same. Okay, then and this is a chaotic set, because what you have here, there is a needle. Then there is an open set of initial conditions that are living along the needle. Then you look at the pre-image of the needle. There is a pre-image here that goes there, another pre-image here. Then there's another one, the second, third. Then you look all the pre-images of that's going into the needle, and then you have to live around the needle. Then that's when you look at this pre-image that I'm talking, you're taking open sets. When you're talking open sets, you take them densely. What remains is a chaotic saddle. And this chaotic saddle, it's here. It looks like a chaotic attractor. Really, it does. Okay? You need to go much beyond in order to see the open sets that are coming into the needle. Okay? That's what it is. Then the dynamics, if you measure here, finite Lyapunov exponent here and there, the same. That's what it is. Okay.
Professor Lakshmanan has a question. Sujit, Professor Lakshmanan has a question.
I have a question. In your bifurcation diagram, transient chaos seems to occur essentially during periodic windows.
Yeah.
Why is it so?
Now, you mean what happens in the periodic windows? That's what you're asking?
Yeah.
No, the periodic windows, what you have a chaotic saddle too. Okay? And
no, those are all periodic windows, no?
yeah, this is a periodic window. This is a period 7 window that you have.
Yes.
Yeah. No, what I was saying here, what's happening here, if you take it, you see all the way, what you have here what looks like chaos. Indeed, chaos, if you take a value of the parameter for which the trajectory is chaotic, then you have, for that value of the parameter, you have infinite number of aperiodic trajectories. Also, you have an infinite number of countable periodic ones. Anyway, but if you take a value for which you have chaos, arbitrarily close, any value, you choose any value here. I take another value here. Arbitrarily close will be a window. Arbitrarily close, okay? Then the windows are dense in the parameter here. In each window, you have a chaotic set. Here, okay? Then there's a chaotic saddle. And if you do the machine learning, because if I train in chaotic saddle, I train here in the crisis region. I take 3 values in which there is crisis. Then I can, if I choose this value of the parameter, I'm going to have the chaotic saddle here. And we call, I wrote paper in 1987, I think, we call this snapshot attractor. You don't see the periodic course, but you see the chaotic saddle here. Then this is a little bit into the dynamics, okay? Then, and that's what is occurring, okay? I can train the machine learning and get all the chaos in the periodic windows. Then the machine learning is going to be blind to the periodic windows. And that's what makes sense, because I cannot train the machine learning in a periodic window, because the number of points I have here is small. Look here, I need the time series to be long. Suddenly I have 7 points here if I choose a parameter there, okay? Then I choose in a chaotic region, and I can make them predict any of the chaos as well, chaotic cell. And this is quite interesting, by the way.
Okay, thank you.
Okay.
In machine learning prediction, what will be your suggestion of choice of the reservoir? In the,
I'm having problem to understand. What's the prediction, what you said?
in the machine learning prediction,
Yeah.
what will be your suggestion of the choice of reservoir? Is it a nonlinear oscillator or a network of oscillators?
It does not matter.
Ah.
It does not matter. No. Yeah, even
No, will you
yes,
say
I have a friend
will you
in China wants to use this in some nonlinear circuits. That's quite important what he's doing, because there's national applications there, and using them to predict tipping points, a collapse of the circuit, using machine learning and using this input parameter channel. And it's highly nonlinear system, okay, and you can make this prediction. The idea is to predict the tipping point here, okay? This critical transition. That's what we're doing. Yeah.
You mean it could be just a simple nonlinear oscillator? The reservoir could be just a simple nonlinear oscillator?
Of course, yeah, no question.
And the training is done from input to the reservoir or from reservoir to output? Which will be the best one?
Yes.
For training?
Yeah, no, you train, okay? You're feeding data into the reservoir, and then you're getting some output. You get some output, but what you're doing, you're training from data. Once it's trained, then you connect the output to the input, and you have a closed system, fixed set of parameters, and that's what it is. And what happened when I was training for different parameter values, I made sure that each parameter value, the machine learning is making correct prediction about the dynamics. And that was indeed happening. Yeah.
Okay, thank you.
Okay, thank you very much.
Thank you. And I think that's the end of our questions. So we want to thank you for a wonderful talk. And we are delighted to announce that our next webinar will feature Professor Sarika Jalan from Indian Institute of Technology, Indore. She will be speaking on January 27, 2025, at the same time as today's time. Please mark your calendars. And we will, as we take a short break in December to celebrate Christmas and New Year, we extend our warmest wishes to you and your loved ones for a joyous holiday season. Thank you all for your continued support, and we look forward to seeing you in January.
No, I thank you, all of you. I think for the questions. I thank Jürgen also for the organization. My goodness, you're incredible. You're fabulous. Okay, thank you very much. See you.
Thank you.
Okay.
See you.
See you. Bye-bye.